Hello everybody, welcome back to our channel. Today is Friday. We start a new thing, our math A&A analysis and approach series. Okay, so we will try to have the complete looks for the whole syllabus bit by bit. Okay, we'll work on it and you give me some feedback down there, comment down there. We think about how to improve it. Okay, mathematics is different. Okay, you need to understand the theory by doing the example. So in this series, I will try to make it like short notes and then example, and then you need to work on it by pausing the video. So bring out some paper, bring out your calculator. Okay, try to work on it. Okay, I'm sure through doing the example, I'll work with you after showing the question. Okay, and then you learn the theory more. Math is very funny. The theory is little, but you need to work, apply it to examples. Okay, so bring out some paper, you can pause and wait. Okay, we start from SL 1.1, and in the math A&A curriculum is a very good written. Okay, so first is SL and then AHL. They separate it clearly. So SL, the first few section is just SL. Okay, we talk about exponent. Something you learned already in the junior form, but now we need to make it grade 11 and grade 12 more sophisticated. First topic, we are on topic 1. Okay, so called 1. Okay, number and algebra. Now is SL and SL 1.1 exponents. First of all, we need to learn, recall what you do mean by number. Okay, accuracy, decimal place, and significant figures. We have to be very sure about significant figures, especially when you work on the sciences. Okay, IA and EE. Okay, zeros means so the zero is a number. It may not be counted as significant figures in the number. Then what are the rules? I'll show you. For example, you have to think here. Okay, a significant figure is counted from the first non-zero number on the left. Okay, non-zero number on the left. So you did 0.00746. Okay, so significant figure started from 7. Okay, so 7 is the first significant figure, 4 is the second, and 6 is the third. Okay, remember non-zero number first. Okay, non-zero number. So 7,245 is easy. Okay, so the 4 significant figure is 1, 2, 3, 4 is 5. Okay, and all the zeros at the end after the decimal point. Remember, you have to look whether there is a decimal point or not. Zeros after the decimal point count as significant. So 35.3300, these two zero count as significant. So altogether 1, 2, 3, 4, 5, 6, 6 significant figures. But it's different for decimal place. Okay, decimal place counts all the number, no matter zero or not, after the decimal point. Okay, decimal point 0.00746. Okay, 5 decimal place. But if you talk about a simple case, another situation, all zeros after the non-zero decimal point, non-zero number first, are counted as accuracy. So for this one, 0.0074600, this zero before the decimal point, no non-zero number, so we don't count this zero as a significant. So for the significant case, let's just start from 7, 1, 2, 3, 4, 5, 5 significant. But if you talk about decimal place, any number after the decimal point we count. So it is 1, 2, 3, 4, 5, 6. 6 decimal point. You need to be sure about this one, especially when you talk about when you work apply in your physics, chemistry, or biology, I or E. Okay. And this is an example. One thing of everyone know. If it is 4 or above, add 1 to the previous to the left hand side number. If it is 4 or below, don't do anything. Right? So given the number, okay, 74.157. Okay, correct to 2 significant. So you look at the 2 significant number 4, right? Look at the right one, 1 less than 4, less than or equal to 4. Okay, so no need to add. So 74. 3 significant. Okay, 7.74.1. Okay, on the right hand side is 5. Oh, I need to add because it's reaching 5, right? Add, so beyond 74.2. Okay, 4 significant. Look at 74.15. 7 at the right. I need to add again. So 16. Okay, the same is here, but be careful about significant. Okay, remember this decimal, this zero after the decimal point without not before all the non-zero number does not count as significant. So these two does not count. So for the 2 significant, not these 2 zeros, 4. Okay, so at the right hand side, 5 at 0.0015. Okay, 3 significant, 1457 at 146. Okay, 4 significant, 1457 2. No way. Okay, got it. Well done. Okay, so next we talk about representing a very large and very small number. You learned it before because it's scientific notation, but now I tell you why. Because when using a scientific notation, there is no ambiguity in the significant figures. Accuracy is clear. by using a scientific notation. If other way, it has some ambiguity. I will talk about it later. Scientific notation, okay, it is in the form like this: a upon bcd times 10 to the power e, okay, where a is the first non-zero digit in the number. to complicate it. All right, look at the example. 0.001243, okay. We start from the first non-zero digit 1, okay. So it's 1.243. How to make it? Okay, the decimal point has to move to the right by 3, okay. So it's 10 to the power negative 3. Okay? Move to the right, negative. Move to the left, positive. Look at the decimal point. Move the decimal point to the first non-zero digit, okay. So if move left to right by n places, multiply by 10 to the power n. Yeah, big number like this one. 2 million, right? So the decimal point here, you add the decimal point. You see, okay, I need to move 6 places to the to 2, okay? 2.0000, so it's 2.0 times 10 to the power 6, okay? It is confusing whether it should be 2.0, 2.00, it is confusing. This is the reason why I don't like this format. Because in this format, 2 million, I don't know whether your measurement, if this is come from science, okay? Your measurement is to this digit or to that digit, I don't know. So I just bring maybe 2.0, maybe we can say 2 times 10 to the power 6, 2. Okay, if the right work by n places, multiply by 10 to the power negative n because it's smaller. So move the decimal point to the right, okay? 4, right? Then we become 3.24674 times 10 to the power negative 4, okay? And the 0 is a little bit confusing, okay? Here's some room of discussion. Okay, keep the 0 at the end of a decimal number. If it is at the end of a decimal number, keep all the 0, okay? 12.4300, remember this 30 can't as zero figure, right? So keep it, okay? So 1.24300 times 10 to the power negative 1. Sometimes you find it in marking scheme. In math, our marking scheme really like to be shown by zero figure because the accuracy will be clear. And don't skip the 0 or have some room of discussion at the end of an integral number. 1, 2, 4, 3, 0. This 3, do you really measure it to this accuracy? Or just measure to the accuracy of 1000? I don't know. So it's confusing. So I use the least one, the least accurate one. So 1.243 times 10 to the power 6. Okay. Okay, bring out your paper. Now is the example time. Okay, express this one in scientific notation. Pause the video and work on it. Welcome back. Okay, you see the decimal point is here. Move to the first non-zero number. Move to the left by 2, right? So it should be 3.47200 times 10 to the power negative 5. Negative 2 is negative, sorry, it's negative, sorry, I just typo, okay, negative, just move 2 places, 2, sorry, typo, okay, and keep the 0 there, okay, negative 2, I apologize, okay. And next one, exponent with a rational exponent, okay, we want to extend the domain of exponent, okay, the concept of exponent. Before, the definition of exponent is 0, right, a to the power m, it means that m, a multiplied together, right, and a is called the base, and the m is the exponent, right. So it is a positive integer, it's okay, we understand. Okay. How about if it is a negative integer? So we extend it by definition. We said that a to the power negative m is 1 over a to the power m. Very smart definition. So negative integer works. Okay. How about the 0? 0, you know, it's not positive or negative. So we have to define a to the power 0 is 1. So before we have the natural definition by positive integer, now we have a negative integer is 1 over, and the 0 is 1. Okay. So all the integer have definition, and then we want to extend it to rational number. Do you remember what is rational number? A rational number can be written as a p over q, where both p and q are integers. Okay. Okay, then we want to extend the exponent to rational number, just 1 over q. What do you mean by 1 over q or 1 over m? A to the power 1 over m, you said that is the mth root. Mth, I remember square root is 1 over 2, cubic root is 1 over b. Okay, I got it. So it is the concept. So square root m is the mth root, is the reverse process of exponent m. So a to the power m is b, then a is equals to b to mth root of b. Okay, so we include it. Okay, so try to show it thing. And I tell you one thing, okay, for the show question, make it as low as possible. Make your, don't jump any step because it is a show question. Okay, try to write as much step as possible. Okay, pause the video and work on it. Welcome back. Now you check in time. Okay, first make a 1.5 at 15 over 10, right? Then 3 over 2. Then look at the question. Okay, I will take out the square. So 1 over 2 take out. Okay, x cubed to the power 1 over 2. 1 over 2, I remember this one is a square root. That's the point. So remember this one is very clumsy. Don't jump the step from the first to the end because the answer is given to you, right? So in IBDP, whenever it's a shown question, okay, remember to do it with a lot of steps. Although in daily life we don't do so many steps, but as an exam question for the shown question, do as much step as possible. And then the law of exponent with rational exponent, the laws, okay. Just remember one thing: a to the power x plus a to the power y. No law. Very simple. No law for this one. Some of the law is just differential, right? Minus x 1 over x. And if two exponents with the same base are multiplied together, just add the exponent. Right? And they divide each other, just subtract the exponent. If it is exponents, then multiply the exponent. If they have the same exponent but different base, just multiply the base. Okay? Also divide the base. Okay? And then just remember for the even integer, we will encounter it a lot of time. Even integer b, okay, and then negative sign will disappear. If this is odd integer, the negative sign survive. Okay? And we can apply this concept to square root third as an example. So square root x square is 1. Okay, and x over square root x is square root x. Square root x over x is 1 over square root x. And then square root x times square root y is two the same exponent, right? So square root xy. Subtraction is the same. Remember, plus or minus, no rules. So to this rule, you just work on the example and pass it more, okay, and then you get used to it quickly. Also remember the law. No law for ax plus ay, plus or minus 2 exponent. No rules again. Okay, try to work on it. Simplify this one. Pause the video and work on it. Welcome back. It's the checking time. Yes, first simplify each of them first. Okay, simplify them. Take out the 25 become 5. Take out the 16 become 4. Okay? And you find out they're the same. Square root x and square root y the same. So make them the same denominator 4. So the first one becomes 20 over 4. And then subtract the numerator. 20 minus 1 is 19. Excellent. You got it. Well done. Next one, okay, rationalize the denominator. We don't want irrational number in the denominator is not preferred because we don't have this concept. Okay? You said that divided by 3, I understand. Separate the thing into 3 parts. Right? Divided by 2, okay, I understand. Divided by 1.23, I understand. Multiply by 100 and then divided by 123 parts. Okay, I understand. But divided by pi, I don't understand. Divided by square root 2, I don't understand. So for the division, if the denominator is irrational number, then the concept will be a little bit confusing. So we don't like it. So we rationalize the denominator with the third. Okay. It's my understanding. The university they have different idea about this. In the IB level is enough. Okay. We need to rationalize the denominator. It will be said clearly in the examination, and in the solution guide already said the denominator is rationalized. But actually, when you hand out your result, you can have the one that have a irrational number in the denominator is also okay. Unless the question specifies rationalize the denominator. Rationalize the denominator, make the denominator real without square. How to do it? For example, 1 over square root a. We sacrifice the numerator. Multiply it by square root a over square root a. The denominator becomes a and the numerator becomes square root a. But square root a is okay, right? In the numerator, I don't divide. Okay? It's just a number. Irrational number is okay. And then we call the identity. X plus y, x minus y, x squared minus y. So how to use this way? Apply to a square root a plus square root b. Multiply by square root a minus square root b. And it becomes a square root a squared minus square root b squared. Bingo, a minus b. Wow. We can rationalize this complicated stuff by multiplying another complicated stuff. Remember, plus multiply by minus, multiply by plus. Okay. For example, we have a string of ax equal y. What's that? Okay. And then change the form of a to this one. And then move it to the right hand side. Wow, very complicated. But it's okay. We learn it how to rationalize the denominator. Multiply it by plus b, then minus b. So we have the sign minus but. Very high order sign. Not plus or minus, it's minus, but it's all magic. Okay? So the denominator becomes a minus b. So the denominator is rationalized. Bingo. Although we sacrifice the numerator. The numerator is complicated, but we said it's okay. So how do try to find excess function with a rationalized denominator? This is a past paper. Okay. Pause and work on it. Welcome back. Okay. Checking time. Remember, tackle this thing first. Make it simplify this for people moving to the right hand side, that will be very complicated. Okay, work sum on the left hand side first. Okay? The same denominator, and then move the square root 5 up. Okay, and then become 1 minus 5 square root 5 over 5, right? And then move the whole thing to the right hand side. Let's flip the fraction. Okay, and then multiply. Oh, the denominator is 1 minus 5 square root 5 is okay. Then multiply by 1 plus 5 square root 5. Although a little bit comes here. Okay, so 1 square minus 5 square root 5 square. Okay, 5 square is 25. Square root 5 square is 5 because 25 multiplied by 5 is 125. And 1 minus it, so negative 124. Okay. And the numerator is easier, just do some simplification. And then there's some rules that can help us to solve the equation and whatever. I found out some rules that can help us to tackle the passive about exponent. Common factor. Fairly simple. X to the power a multiplied by 6x to the power negative a is 1. Everyone knows it cancels out, right? A over a. But it is important, useful to us. Okay. Take out the common factor with the smallest exponent. Eliminate the common factor in the numerator and the denominator. For example, this one. Because we have a 1 over xa, okay? And xa in the numerator, then cancel them out. What remains? Xb. This one is different. Numerator more, denominator more. 1 over xa plus b, okay. Xa, okay. Remember, 1 over x to the power b, okay. So this is a very simple but important fact. Okay, okay, simplify this one. Okay, welcome back. Okay. So first of all, remember this negative. Does it survive? Negative integer. Yes, it survives. Okay. So it survives with negative. And then at 2012, 2011, this one more. So 1 over 3 win. Okay, 1 more, right? So negative 1/3. And the common base or common exponent. So the next step is to make sure something that is useful. Okay, or if a is not 0 or 1, okay, a to the power x equal a to the power y, it means x equal y. Yes, everyone knows it, right? So you change it. Change it to the same base. And then the exponent will be equal. Very useful. Okay? Make the bases of exponent the same. Okay, for equation with terms are different bases. Okay, of exponent. Make the bases the same. Make it as small as possible, not big. Make it small. Okay. I want a larger integral exponent. So 16 to the power x, make it 4 to the power 2x. 27 x, make it 3 to the power 3x. Okay. And then make the form ax equal ay. And then x equal y. Excellent. And if the base you can't make it the same, then make the exponent the same. For example, 5 to the power 2x, you can make it 25 to the power x. Okay. And if the other thing is also 25 to something, then x will be equal to that thing. Right? So it's the trick. Okay. Make the base or the exponent the same. See which one is easier. Look at here. Try to solve this equation. Remember the rules. Make the exponent as small as possible. No. Make the base as possible. Make the base small. Sorry. Make the exponent big. Okay. Welcome back. Okay. Now you're checking them. Okay. Make them all to the power 2. Okay. Base 2. Base 2, 2 square, 2 cube, 2 4, right? And then 2 to the power 2x to the power 9x, right? And then add them together to the power 11x equal to the power 4. So 11x equal 4, x equal 4 over 11. How can you get this one without this skill? Right? Impossible. Right? But if you have the skill, all the thing is straightforward. So remember the skill, make the base or make the exponent the same. And then some common mistake, really common mistake. You use the wrong rules. Ax over ay cancel out the x. A become x over 1. No, it should be a to the power x minus 1. Right? Subtract the exponent. Ax over ax cancel out becomes 0. No, it should be 1. Cancel out 1 over 1. Right? And then plus or minus, no rules. Okay. And then this thing is very confusing. 3a, b, maybe a cube. No, 3a and 2b. Don't forget your junior knowledge, right? 6ab. This one also. X over x cubed. No, 3x and 2x over x squared. 3 to the power n times 4 to the power n, and then 3 times 4 n plus n. No, just 9 either way. The same exponent, so the same exponent, just multiply the base, so 12 to the power n. And then this one also, wow, 3 to, wow, 27. No, they have different exponent, can't add together, right? So change the base the same and then add the exponent. Shall we work on it? Okay, express this one as a fraction. Welcome back. Okay, just checking time. Okay, just by definition, 1 all is 1 over, but be careful. 1 over 1. Same denominator. And then flip it up. So it's AB over B minus A. You got it? Yes, it's tricky. Even the question looks simple. Be careful. So thank you for your going through the journey with me for SL 1.1. It's a good start, and you'll find now working at the example. I hope it can help you. Comment down there to say whether it helps you or not, or you want more example or whatever. Okay. I hope I cut the thing into different small parts with a small example. It can help you. Okay. Okay. See you next Friday for Mathematics A and A. Bye.